Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on November 5th, 2025, just yesterday. This paper reports an intelligence crossover. When unique data is limited, diffusion language models consistently surpass autoregressive models with more training, including a 1.7 billion diffusion model trained with about 1.5 trillion tokens on 10 billion unique Python tokens that overtakes a strictly matched autoregressive coder, and a 1 billion model that reaches over 56% on HelloSwag and over 33% on MMLU using only 1 billion tokens. The paper is titled, Diffusion language models are super data learners, and as we will see, the implications for data-efficient training are quite significant. Also, the authors shared a full repo. You'll find an optimized Megatron LM training codebase for Diffusion LMs, a Mega DLMs implementation, and utils scripts for downloading checkpoints, inference, and format conversion. They provide all training checkpoints and logs, plus extensive resources for ablations across data budgets, quality, sizes, sparsity, masking, dropout, and coder scaling. Alright, Figure 1 shows the crossover, which means the point where diffusion overtakes autoregressive as unique data shrinks. The rows sweep from 0.5 billion to 96 billion unique tokens, and the red diffusion curves climb faster at small budgets. As unique data grows, the crossover moves later, so blue autoregressive keeps up longer. Validation loss tells a different story, spiking for autoregressive with repetition while diffusion stays stable. Figure 2 shows that higher data quality helps both model families, but it delays the crossover where diffusion pulls ahead. The rows compare low, medium, and high quality, while holding 1 billion unique tokens constant, so the curves isolate quality effects. Diffusion keeps improving across epochs, whereas autoregressive gains taper as repetition grows. The right column highlights that validation loss trends do not match accuracy, which means lower loss can coexist with worse benchmark scores. So, Figure 3 shows that increasing model size shifts the crossover earlier, because larger diffusion models keep learning from repeated tokens, while similarly sized autoregressive models saturate. The top rows sweep from 1 to 8 billion parameters, and the red diffusion lines climb steadily across epochs. The bottom put together row stacks the trends, and darker curves, meaning larger models, push diffusion higher. Autoregressive curves rise then flatten as overfitting sets in, which means the model memorizes repeats and its accuracy stalls. Well, Figure 7 shows that diffusion models overtake autoregressive coders on code tasks once training repeats about 1 trillion tokens. This figure, which spans 3 panels, contrasts downstream accuracy with validation loss. The left and middle panels track pass at 1, which means the fraction of problems solved on the first attempt, and the pink diffusion curves climb, while the green autoregressive curves plateau. The right panel reports validation loss, and the green line remains lower even when diffusion wins on accuracy, highlighting the diagnostics caveat. Together, these traces indicate an early crossover that likely widens with longer training, because diffusion keeps learning from repeats. So Table 1 summarizes the evaluation protocols, which clarifies exactly how the scores in the plots were computed. Completion close means the model selects the right ending, while generative means it must produce code or text, and per character normalization divides loss by character count for fairness. The table lists shot counts from 0 to 5 and specifies validation versus test splits. Codebase entries note which tooling executed each benchmark, so comparisons stay consistent. Wrapping up, 2 takeaways stand out. Diffusion models extract more capability per unique token in data-constrained training, and the edge comes from any order modeling, super dense bidirectional denoising, and Monte Carlo-style augmentation. The broader implication is clear. In a data-scarce era, training strategy and diagnostics must shift. That is it for the AI Research Roundup. I am Alex. Thanks for listening.